What happens when you crush a star until its atoms collapse, forcing protons and electrons to merge under densities never before seen on Earth? You get a neutron star, a celestial object so extreme that a single teaspoon of its matter weighs more than a mountain. Yet, despite our fleet of telescopes, satellites, and supercomputers, we still don't truly know what lies at its heart. Some say it is a soup of deconfined quarks, others propose exotic particles unknown to science, a few even suspect the laws of physics themselves begin to break down. The reality is far stranger than fiction, which is why the neutron star remains the most baffling object in the cosmos. It's a long story, but we'll begin our journey in the realm of dreams, and before we dive deep, don't forget to like and share. Most people immediately wonder about the exotic core where physics fails, but before we go that deep, the surface and upper crust are already difficult enough to comprehend. The surface of a neutron star is nothing like the solid ground we know. Even though the crust is only a few hundred meters thick, it contains more mass than an entire planet. This layer is primarily composed of tightly packed atomic nuclei, the same building blocks of atoms on Earth but squeezed in ways our world has never experienced. On Earth, a nucleus is tiny compared to the vast space around it where electrons buzz. On a neutron star, that empty space is stripped away. The crust jams matter together so tightly that the nuclei sit cheek to jowl, leaving almost no gaps. To put it another way, if you could hold a teaspoon of this crust, it would weigh as much as Mount Everest. Even this thin outer shell far exceeds any density we encounter in daily life. The very outermost layer might still resemble heavy iron. Atoms with clinging electrons, but just a few centimeters down, the pressure becomes so extreme that atoms are crushed, electrons are forced into nuclei, and matter transforms into a denser state. Dozens of meters into the crust, almost every nucleus sits in a sea of dripped neutrons. This is a strange playground where everyday chemistry ceases to have meaning. The behavior of this layer under pressure is equally anomalous. Because neutron stars rotate so rapidly, they occasionally experience starquakes, abrupt ruptures where the planet-sized crust cracks like an eggshell. While Earth's tectonic plates move slowly over millions of years, the shell of a neutron star can snap in milliseconds, releasing a colossal amount of energy. Astronomers have linked these crustal fractures to glitches in a pulsar's rotation rate, proving that even this thin skin dictates the behavior of the entire star. The crust also acts as a heat shield. Born in a supernova, a neutron star is unimaginably hot, with a newborn core reaching trillions of degrees. How that heat escapes is controlled by the crust. Its density and composition determine whether the heat seeps out slowly or gushes forth. If the outer layers allow ghost particles called neutrinos to escape in bulk, they carry away the star's thermal energy much faster than our models predict. Furthermore, the sheer strength of this material is staggering. While researchers once thought the crust might be unstable, simulations show it may be the strongest substance in the universe. Under intense gravity, atoms are locked into a hyper-strong lattice that is billions of times harder to break than steel, allowing the star to maintain its near-perfect spherical shape despite its ferocious rotation and magnetic fields. As the outer crust transitions into the inner crust, matter becomes even more bizarre. At this boundary, where the density exceeds that of an atomic nucleus itself, new structures emerge that scientists call nuclear pasta. Here, matter is forced into shapes resembling spaghetti, lasagna, or gnocchi. Even without diving into the core, this pasta layer challenges our understanding of reality. Perhaps most surprising is that the skin, though as heavy as a planet, is merely a thin wrapping around a sphere only 20 kilometers in diameter. The true mystery lies deeper, where the majority of the mass resides. The neutron star is what it is because of the shell it anchors the magnetic field, shapes the radiation pulses, and guards the exotic matter within. Deep inside the star, matter organizes itself in ways no one could have imagined. This nuclear pasta layer arises from a tug-of-war between two fundamental forces, the strong nuclear force, which tries to clump protons and neutrons together, and the relentless pressure and density of the star, which forces matter to spread out as efficiently as possible. Neither force can win completely. As a result, matter organizes into strange, periodic structures, not spheres, but long rods, flat sheets, or irregular clumps. Advanced simulations from the 1980s and 90s first predicted these shapes. At specific densities, spaghetti, rods, is the most energy-efficient form. At higher densities, it flattens into lasagna, sheets, or becomes gnocchi, blobs, or honeycomb-like channels. The variety is so vast that researchers use Italian pasta names to categorize them. The significance of nuclear pasta goes beyond its playful name. First, it may be the strongest material in existence, potentially billions of times stronger than steel, which explains how neutron stars maintain their shape at hundreds of revolutions per second. Second, it affects the flow of heat. These complex structures scatter particles moving through the crust, acting as an insulating layer that traps the internal heat of the star. Third, it interacts with the magnetic field, which can be trillions of times stronger than Earth's. The conductivity of nuclear pasta, influenced by its bizarre geometry, may trap magnetic field lines, causing them to twist or knot, which leads to the explosive flares and glitches we observe. Some scientists even argue that the structural complexity of nuclear pasta, involving millions of particles in intricate 3D patterns, rivals the complexity of biological macromolecules, as if it were a different expression of the material of life born under entirely different conditions. While we cannot extract a sample or replicate these conditions on Earth, heavy ion collisions in labs provide tantalizing clues that these structures are real. We usually think of fluids as water or air, and we view friction as a universal trait that slows motion and drains energy. But inside a neutron star, matter may become a superfluid, a quantum state of matter that is frictionless and never loses energy. This is one of the most alien concepts in physics. On Earth, we see this in liquid helium near absolute zero, where it can climb up the walls of a container or flow through microscopic cracks without resistance. In a neutron star, the neutrons are squeezed so tightly that their quantum nature takes over. They no longer behave as individual particles but move in a single, coordinated quantum state. The biggest clue for this is the pulsar glitch. Most pulsars slow down over time as they lose energy, but occasionally, they suddenly speed up. The leading explanation is that while the crust is slowing down, the superfluid interior maintains its original high speed due to its lack of friction. Eventually, the speed difference becomes too great, and the superfluid suddenly transfers a kick of angular momentum to the crust, causing the rotation rate to jump. These superfluids store their rotation in quantum vortices, tiny, tornado-like structures. A single star might contain billions of these vortices, all aligned with the rotation axis. As the star slows, these vortices migrate or snap, and each shift sends a shock wave to the crust. Furthermore, a superfluid might coexist with a superconductor. While neutrons become a superfluid, the small population of protons in the same environment may form a superconducting current that flows without resistance. This hybrid state is likely the key to how neutron stars lock in and maintain their massive magnetic fields, especially in the case of magnetars. When you hear superconductor, you might think of maglev trains or lossless power lines. The interior of a neutron star makes these look like toys. Protons in the core form what is likely the most powerful superconductor in the universe. On Earth, this requires extreme cold. In a neutron star, it is the standard state. Though protons are positively charged and should repel each other, the crushing density forces them to form Cooper pairs, allowing current to slide through the core without any resistance across a 20-kilometer span. This superconductivity pins the magnetic field lines into quantized tubes. The movement or snapping of these tubes can cause the surface magnetic fields to snap and reconnect, triggering the massive X-ray and gamma-ray flares we see. In physics, an equation of state, EOS, is the formula that describes the relationship between pressure, temperature, and density. We have reliable equations for the air we breathe and the plasma inside the sun, but for the heart of a neutron star, the equation of state remains the ultimate frontier of nuclear physics. When the conversation shifts to the internal state of a neutron star, the equations of state, EOS, become one of the greatest unsolved mysteries in modern physics. We find ourselves in a regime where no known laboratory-tested equations fully apply. The core densities here can reach several times that of an atomic nucleus. It is no longer a matter of being extreme, it is the equivalent of squeezing the entire human race into a volume the size of a sugar cube. At these scales, matter may behave in ways we have never envisioned, and traditional nuclear theory struggles to penetrate. Physicists have proposed various candidates. Some assume a core dominated by neutrons with a light dusting of protons and electrons, while others introduce exotic components like hyperons, kaon condensates, or even deconfined quarks. Each unique composition yields a different EOS, predicting distinct radii and thresholds for gravitational collapse. In essence, the stiffness or softness of the EOS dictates the size of a neutron star for a given mass. A stiffer equation supports a larger radius, while a softer one results in a more compact star. Observation is our only path forward, measuring precise masses, radii, and dynamical behaviors. We have observed neutron stars exceeding 2 solar masses without collapsing into black holes, a fact that demands the true EOS be sufficiently stiff. Conversely, some data suggests radii as small as 11 kilometers, hinting at a softer tendency. Reconciling these 2 points is like trying to force together pieces of a jigsaw puzzle that don't quite fit. The advent of multi-messenger astronomy, specifically neutron star mergers, provides a new lens. The tidal deformability recorded in gravitational waves as seen in the landmark GW170817 event acts as a diagnostic for whether the stellar matter is stiff or soft. While it has ruled out several extreme models, a clear winner has yet to emerge. Simultaneously, NASA's NICER mission on the International Space Station uses X-ray pulse profiling, accounting for general relativistic light bending around thermal hotspots, to map mass and radius. These results further pressure the EOS, eliminating extremes but leaving a significant gray zone of uncertainty. This tug-of-war is vital because it concerns the fundamental building blocks of matter. If quarks appear at the core, the EOS would diverge sharply from that of pure nucleons. If hyperons or kaons emerge, the pressure-density relationship changes again. Neutron stars are cosmic laboratories performing experiments we simply cannot replicate on Earth. This leads to the maximum mass problem. At what point does a star inevitably collapse? Some calculations suggest a limit near 2.0 solar masses, while others push it toward 3.0. If a particularly heavy neutron star is confirmed, any EOS incapable of supporting it must be discarded. Even a tiny adjustment in the calculated nuclear forces can shift the predicted radius by kilometers or double the maximum mass. This sensitivity makes neutron stars the ultimate testing ground for nuclear physics, yet keeps them shrouded in uncertainty. When we speak of sound, we think of pressure waves in air or water. But in physics, sound speed is a direct proxy for the stiffness of the medium. In air, it is 343 meters per second, in steel, it reaches 6 kilometers per second. Push this logic to the densities of a neutron star, and the speed of sound may exceed 30% of the speed of light. At these densities, neutrons are so tightly packed that any compression triggers an instantaneous, massive rebound. These relativistic sound waves surge through the core at roughly 100,000 kilometers per second, crossing a 20-kilometer star in less than a millisecond. Since sound speed is directly linked to the EOS, we use evidence from gravitational waves and pulsar timing to infer that internal sound speeds may approach the relativistic limit allowed by causality. These speeds likely vary across layers from a fraction of light speed in the crust to nearly 1/3 in the deep core. If a phase transition occurs, the sound speed might even jump, potentially triggering starquakes. These sudden releases of stress create seismic oscillations that, unlike Earth's, unfold in milliseconds with energies far beyond our comprehension. Even the giant flares from magnetars might be triggered by these internal acoustic vibrations. More surreal still is the temperature. A newborn neutron star can reach 1 trillion degrees. In this quantum-dominated thermal sea, sound waves are no longer simple pressure disturbances but coordinated quantum excitations. We cannot hear them directly, but the star's vibrations shout into the universe via gravitational waves, allowing detectors like LIGO and Virgo to catch the echoes of matter under the most extreme conditions. While we assume neutron stars are made of neutrons, the presence of strangeness introduces the hyperon puzzle. Hyperons are heavier relatives of protons and neutrons containing at least one strange quark. On Earth, they decay instantly, but the immense pressures inside a neutron star might stabilize them. The trouble is that hyperons provide less outward pressure than nucleons. If they appear in large numbers, the star should soften and collapse much sooner. Standard hyperonic models suggest a maximum mass of only 1.5 solar masses, yet we observe stars at 2.0 solar masses. This slap in the face to theory suggests either we are missing repulsive forces between hyperons that stiffen the EOS, or perhaps a transition to quark matter occurs simultaneously to offset the softening. These exotic particles also change how neutrinos are produced, potentially accelerating the cooling of the star, a trend that matches some observations. While heavy ion collisions in particle accelerators help us infer hyperon behavior, those experiments last only a fleeting moment, whereas a star lives for eons. The subtle shapes of gravitational waves from mergers may eventually reveal whether these strange relatives are truly hiding inside. If hyperons are the strange relatives, kaons are guests from another family entirely. Composed of a quark and an anti-quark, kaons are highly unstable on Earth, yet in the dense core of a neutron star, they might form a Bose-Einstein condensate, a stable quantum liquid. This condensation occurs because, at extreme pressures, it becomes energetically cheaper for the star to store charge and energy in kaons rather than nucleons. However, this comes at a cost. Kaon condensates soften the equation of state, making the star more susceptible to collapse. This is the kaon mystery. Theory suggests they should be there, but if they were too prevalent, many observed neutron stars shouldn't exist. Kaons would also open new neutrino cooling channels. Some bolder theories even view kaon condensation as a stepping stone toward a full transition to quark matter. Imagine unzipping a neutron so that its constituent quarks roam free. This is the quark matter core. On Earth, quarks are always confined within larger particles by the strong force, but the crushing density of a neutron star may break these bonds, creating a fluid of deconfined quarks. While colliders create a quark gluon plasma at ultra-high temperatures for a trillionth of a second, neutron stars might simmer this quark soup at high density for billions of years. If quark matter exists, it could explain small but incredibly dense hybrid stars that are more compact than standard neutron stars. An even more radical hypothesis suggests strange quark matter, a mixture of up, down, and strange quarks might be the most stable form of matter in the universe, potentially even infecting ordinary matter upon contact. Though speculative, quark matter might also exhibit color superconductivity, where quarks form pairs analogous to electrons in a superconductor. This would alter everything from the star's magnetic field evolution via a color Meissner effect to its cooling rate. Ultimately, a neutron star walks a tightrope between stability and collapse. Decades ago, we thought the mass limit was around 2.0 solar masses, but precise observations of pulsars like PSRJ0740 plus 6620 and PSRJ0348 plus 0432 have pushed that boundary to 2.14 or even 2.23 solar masses. This is a massive distinction on the blade's edge of black hole formation. If these heavy stars are the norm, our understanding of dense matter is incomplete, or there is an undiscovered pressure mechanism, perhaps rotation-induced stability or twin stars. The twin star hypothesis suggests two stars could have the same mass but different radii due to different internal phase transitions. If we see a branching in the mass-radius relationship, it would be smoking gun evidence for a phase transition. We also see this internal complexity in glitches, sudden, millisecond-long speed UPS in a pulsar's rotation. These are likely caused by the unsticking of quantized superfluid vortices in the interior, suddenly transferring angular momentum to the crust. Furthermore, the magnetar-class stars with magnetic fields so strong they could wipe a credit card from the distance of the Moon shows us that magnetism can warp space-time and the very shape of atoms, potentially altering the EOS itself. From the crushing of the strong interaction to the cooling whispers of neutrinos recorded in the Cassiopeia remnant. Every observation brings us closer to understanding the heart of the neutron star, a place where the laws of physics are pushed to their absolute breaking point. Phase transitions within a neutron star may also suppress certain cooling channels, effectively trapping heat and keeping the star warm. In magnetars, the intense magnetic field can even polarize neutrinos, creating a cooling curve that is entirely unique. While the detection of neutrinos from supernova 1987A confirmed the broad framework that neutrinos dominate the energy loss in a collapsing star, a neutron star continues to produce them for tens of thousands of years after its birth. If we could capture even a fraction of these thermal neutrinos, we would gain a direct window into the hidden processes of the core. This leads us to a hypothesis that is as haunting as it is fascinating, the idea that the core consists of strange quark matter. If strange matter is actually more stable than ordinary nuclear matter, the Bodmer-Witten hypothesis, then what we call neutron stars might actually be strange stars. In this radical scenario, a single drop of stable strange matter coming into contact with ordinary matter would infect and convert it entirely. From the outside, a strange star would look nearly identical to a neutron star, but for the same mass, its radius would be slightly smaller and it would cool much faster. Some observed objects with anomalously rapid cooling rates have led researchers to wonder if they are indeed strange stars masquerading in neutron star clothing. While terrestrial particle accelerators have yet to find definitive evidence of strangelets, a transition to a strange state within a neutron star could release enough energy to trigger a gamma-ray burst. At even more extreme densities, pions, the particles that mediate the force between nucleons, might not only emerge but condense into a macroscopic quantum state known as a Bose-Einstein condensate. A pion condensate would drastically alter neutrino pathways, accelerating cooling and softening the equation of state, which would lower the maximum mass the star can support. Under the influence of a strong magnetic field, this condensate could become anisotropic, making magnetar outbursts and star quakes even more violent. The theoretical threshold for pion condensation remains a subject of fierce debate, reflecting just how little we truly know about the physics of the deep interior. The early onion-like models of a neutron star consisting of a simple crust, an outer core, and an inner core can no longer describe the true complexity we are discovering. Near the bottom of the crust, the nuclear positive phase blurs the boundary between the solid shell and the liquid interior. In the outer core, superfluid neutrons and superconducting protons likely coexist, perhaps interspersed with hyperons, mesons, or clusters of deconfined quarks. Whether the inner core is a dense nucleon phase, a quark soup, or a more exotic condensate remains an open question. Phenomena like starquakes and rapid cooling suggest that internal stress and energy channels are far more intricate than a simple layered sandwich. NASA's NICER radius measurements and the tidal deformability data from gravitational waves are slowly moving the pieces of this puzzle into place. The final picture may reveal that the internal recipe varies depending on the mass, age, and magnetic field of the star. Since the first direct detection of gravitational waves in 2015, they have become our most powerful probe. As two neutron stars spiral toward a merger, their mutual gravity stretches them like rubber balls. This tidal deformation leaves a signature in the gravitational wave signal. By analyzing it, we can determine if the matter is stiff or soft, thereby constraining the equation of state. The landmark GW170817 event in 2017 combined gravitational waves with electromagnetic observations, launching the era of multi-messenger astronomy. Future, more sensitive detectors LIGO, Virgo, CAGRA, and the planned Einstein telescope will expand our sample size to the distant universe and may even capture the high-frequency scream of a hypermassive neutron star in the milliseconds before it collapses into a black hole. While we cannot see these 20-kilometer dots directly, missions like NASA's NICER allow us to feel their contours using X-rays. By tracking hotspots on a pulsar's surface as it rotates and accounting for how general relativity bends that light, scientists can reconstruct the star's mass, radius, and surface geometry. For instance, pulsar PSRJ0030 plus 0451 was found to have a radius of about 13 kilometers, but its hotspots were surprisingly complex, not simple polar caps, but elongated crescents. This suggests the surface magnetic fields and electrical currents are much messier than we once thought. Combining NICER's data with radio timing and gravitational wave constraints has already ruled out several overly soft models, confirming the existence of the two solar mass club. In the past, we believed neutron star masses were concentrated between 1.2 and 1.5 solar masses. Today, we keep finding heavy weights that push the boundary to 2.0 or even higher. Their existence implies that either core matter is stiffer than imagined or there is an additional support mechanism, such as a phase transition to a color superconductor. These heavy stars also influence how we interpret the fate of a merger, whether the result is an immediate black hole or a briefly surviving, hypermassive neutron star depends entirely on this true upper limit. The textbook version of a neutron star says it cools via neutrinos in its youth and photons in its old age. In reality, some stars cool too fast, while others stay unexpectedly warm. The 4% temperature drop over a decade in the Cassiopeia remnant fits the profile of a neutrino surge triggered by neutron pairing in a superfluid. Meanwhile, hotter stars might be reheated by magnetic field stress or starquakes. Each cooling curve is essentially a medical checkup report, with every data point casting a vote for what lies inside. In nuclear physics, a critical but abstract quantity is symmetry energy, the energy cost of turning a balanced mix of protons and neutrons into the neutron-rich matter of a star. While heavy ion experiments on Earth can measure symmetry energy at normal densities, the extrapolation to the interior of a neutron star is vast. Bridging the gap between lab experiments and astronomical observations is our only hope. Is a neutron star a solid crystalline sphere or a strange liquid? The outer crust is undoubtedly a solid lattice. Deeper down, as nuclei dissolve, it behaves more like a liquid. But the deep core is a battlefield of theories. Is it a rigid lattice of quark crystals, or a ghostly liquid of superfluids and superconductors? The answer might be a hybrid, a mix that provides the rigidity to support the massive crustal stresses of a magnetar, while maintaining the superfluidity needed to explain pulsar glitches. Some neutron stars spin hundreds of times per second, with the fastest exceeding 700 Hz, where the equator moves at nearly a quarter of the speed of light. The limit of this rotation is a balance between gravity and centrifugal force. Most equations of state suggest a breakup speed of around 1000 Hz, yet we have never found a star spinning that fast. Perhaps gravitational waves act as a brake. Any tiny mountain on the surface, even a centimeter high, would radiate energy and slow the star down. Or perhaps the internal coupling between the superfluid and the crust acts as a hidden speed limiter. We will leave our journey into the heart of the neutron star here for today. I hope these insights give you a sense of the incredible physics playing out in the cosmos while you dream. Have a wonderful day, and we will see you in the next episode.